Here is a question that sounds simple. What are numbers actually made of? Take 12. You can break it into 2 times 6. Or into 3 times 4. 2 different starts. But keep breaking every piece, and both roads end at exactly the same 3 bricks. 2, 2, and 3. In this lesson, we find the building blocks hiding inside every number. Those bricks are called prime numbers. A prime number is a number greater than 1 that has exactly 2 factors, 1 and itself. Look at 7. Its only factors are 1 and 7, so 7 is prime. Now look at 6. 1, 2, 3, and 6 all divide it. That is more than 2 factors, so 6 is not prime. Numbers like 6 are called composite numbers. And the number 1 is special. It has only 1 factor, itself, so it is neither prime nor composite. Along our number line, the primes light up like this: 2, 3, 5, 7, 11, 13, and they go on forever. Let us play with a small collection of primes: 2, 3, 7, 11, and 23. Multiply a few of them. 7 times 11 times 23 builds 1,771. Bring in 2 and 3 as well, and the product grows to 10,626. We may also repeat a prime as often as we like. 2, used 3 times, with 1 3, and 7 used 3 times, builds 8,232. So multiplying primes creates numbers without end. Now flip the question. Can every number be broken back down into primes? Let us test that on a big number, 32,760. We will grow a factor tree. Split off the smallest prime that divides it. It is even, so 2 works, leaving 16,380. Still even. 2 again, leaving 8,190. And once more, 2, leaving 4,095. That is odd, so 2 is done. Its digits add to 18, so 3 divides it, leaving 1,365. 3 works again, leaving 455. Next, it ends in 5, so 5 divides it, leaving 91. Finally, 91 splits into 7 times 13, and both of those are prime. Every branch now ends at a prime. The tree is complete. Collect the primes waiting at the ends of the branches: 2, 2, 2, 3, 3, 5, 7, and 13. Now group the repeats. 3 copies of 2 stack into 2 cubed. 2 copies of 3 stack into 3 squared. So 32,760 equals 2 cubed, times 3 squared, times 5, times 7, times 13. This compact form is called the prime factorization, written as powers of primes. And to be sure, multiply everything back: 8 times 9 times 5 times 7 times 13. It lands exactly on 32,760. Here is a second method that keeps everything tidy: the division ladder. Let us factorize 140. At every step, divide by the smallest prime that works. 140 is even, so divide by 2. That leaves 70. 70 is even too. Divide by 2 again, leaving 35. Now 2 fails, because 35 is odd. 3 fails as well, since its digits add to 8. But 35 ends in 5, so 5 divides it, leaving 7. 7 is itself prime, so one last division leaves 1, and the ladder stops. Read the divisors down the left side: 140 equals 2 squared, times 5, times 7. What we have been using is one of the most important facts in mathematics, important enough to be called the fundamental theorem of arithmetic. It says, every composite number can be expressed as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. Notice the 2 promises. First, a prime factorization always exists. That is what our trees and ladders keep finding. Second, it is unique. Apart from shuffling the order, there is only one way to do it. To keep the order tidy, we write the primes smallest first. The first correct proof of this theorem was given by Carl Friedrich Gauss, a mathematician so admired he is called the Prince of Mathematicians. Today we used existence. Why the factorization must be unique is the story of our next lesson. Now for a trap that catches many students. Someone factorizes 12 as 4 times 3, and stops, calling 4 and 3 its prime factors. Check each piece. 3 is prime, that part is fine. But 4 is not prime. 4 is composite, it still splits into 2 times 2. A prime factorization may contain only primes. So keep splitting until every piece is prime. 12 is 2 times 2 times 3. Written with powers, that is 2 squared times 3. The rule to remember: stop only when every factor on screen is prime. Your turn. Express 156 as a product of its prime factors. Use a factor tree or the division ladder, whichever you prefer. Pause the video here, and give it a genuine try before the answer appears. Ready? Let us solve it together. 156 is even, so the smallest prime, 2, divides it, leaving 78. 78 is even as well. Divide by 2 again, leaving 39. Now 2 fails. But the digits of 39 add to 12, so 3 divides it, leaving 13. 13 is prime, so the latter finishes. Collecting the divisors, 156 equals 2 squared, times 3, times 13. Verify it. 2 squared is 4. 4 times 3 is 12. 12 times 13 is 156. It checks out perfectly. Let us gather what we have built. Prime numbers are the building blocks of all numbers. The fundamental theorem of arithmetic promises that every composite number is a product of primes, and we write that product compactly, using powers, with the primes in ascending order. And you now own 2 reliable tools, the factor tree and the division ladder. Next time, we ask why the factorization is unique, and how that uniqueness lets us predict things a number can never do.